Hello folks! How's everyone doing? It's about time to start here. I think I'm a minute or so late, but hopefully it's all good. If you can see me and hear me okay, can you please just say something in the chat? If the sound is bad, I can fix that, make it louder or softer. How are we doing? Way too loud, probably. Maybe that's a little better. People are here, right? Okay, good. Awesome. Saw nothing there first and I was just making sure. So, we are all good. My hair's all messy. Okay. So, for today's tutorial, I basically got a bunch of questions that were submitted. Little tickle in my throat here. A bunch of questions that were submitted that I can definitely start with. If there's anything that I'm doing that doesn't look familiar or you have any questions on what I'm doing, please just pop a little message in the chat, and I have the chat right in front of me, so I should be able to see that right away. Hopefully you can see on my screen a couple of random questions that were submitted to me from previous exams. One thing I just want to warn people about is typically what happens on these sorts of tutorials is people will kind of scour the last 10 years worth of exams and come up with the most obscure and most difficult examples. So sometimes the examples that get asked and featured in tutorials like this aren't really representative of what you can actually anticipate seeing on the final exam, if you know what I mean. Okay, so I'm going to jump right in. The first question I was asked was from the 2019 exam. Actually, I don't even know where these are from. They're sort of just copy and pasted. Some were just submitted to me as screenshots, so they came into my PDF here as screenshots. The first question says, which of the following molecules is optically active? So to be optically active, it needs to be chiral, and to be chiral, it needs to have chiral centers and no planes of symmetry. And that means a molecule like C is out because C has a plane of symmetry while having two chiral centers, making it meso. So that means that compound is not going to be a chiral molecule, therefore it's not optically active. A has no chiral centers, so A is out as well. E has no chiral centers. It kind of looks tricky. It looks like that could be a chiral center right there, but in fact it's not, because we have a methyl and a methyl, and those are the same thing. And when you have two groups the same off the same carbon, it cannot be a chiral center. D, it turns out, is also not optically active. It has two chiral centers here and here, but if you were to rotate that bond around and redraw it, it would look like this, which has a plane of symmetry, which makes this one meso as well. So the correct answer is B, although B is a bit of a weird example, because if you look at B, it doesn't actually have a chiral center in the way that we define them in the course. So I wouldn't, in this year, on like this year's exam, give you an example like this. Keep in mind, different people teach this course in different years, and different things get stressed and different things get taught, slightly different things. But molecules like B can be chiral. So if you were to see a question like 12, which I told you I'm not putting on this year's exam, the only real way I'd expect you to get something like this is by process of elimination, because we know all the other ones aren't. This basically, if you think about these two carbons, they do kind of, it's like a tetrahedral with a spacer in the middle, and those are chiral centers, but we didn't deal with that type of chirality this year. 15 off the same exam says, which of the following carbocations would likely not rearrange? Would not likely rearrange. So carbocations that will not rearrange are ones that are tertiary already, since they're already as stable as they could be. And B is tertiary, so I'd say B is likely to not rearrange. Anything that's secondary is likely to rearrange if there's a rearrangement available. This one is secondary. This one is secondary. This one is primary. So that, like, primary carbocations are really unstable. They're really bad. So if there's any possible way that could rearrange, it will. And this one is secondary as well. So it's the tertiary one that's already stable that isn't going to rearrange. Just to note too that the this video, if you follow the link anytime in the next day or two, whatever, the same link will just bring you to a recording of this, so you can see it later again whenever you want. This question, and I got variations of this question many times. There'll be no reaction or mechanism questions on this exam that involve epoxides. Epoxides are basically like a cyclopropane with an oxygen in the ring. So if you see something like that on any old exam, that is due to a section that we did not cover this year, and you can not worry about it. So this question I'm not going to bother doing. It's reactions that we haven't covered. And I saw quite a number of questions like that submitted, questions where people had seen something on an older exam that wasn't covered in this year's course. Right, so this was another question that was submitted, same thing. So again, you're making epoxides in this example, and so for that reason we can ignore this one as well. All right, so question 7, I guess, I don't know what year that's from. These are popular questions. One of these questions where you have to outline a multi-step synthesis to convert your starting material, whatever it is, to the product over here. And you're not asked for a mechanism, you're just asked for the conditions, like reaction sequence. And there could be potentially a number of correct ways of doing a question like this. But almost always they require at least 2 steps, generally more, or 2 or 3 is typical, sometimes maybe 4. So you can see in this example, we are beginning with an alkane. It's just butane. And the nice thing about only knowing a couple of reactions so far is that the options we have are fairly limited so far at this point. In fact, there's only one reaction we looked at that begins with an alkane. And this is a reaction from Unit 9 which uses a halogen, either bromine or chlorine. If you use bromine, for example, and light or heat, this will do radical halogenation. And chlorine is not that selective. Chlorine will go kind of all over the molecule. So if you use chlorine here, you might expect to get 1 chlorobutane and 2 chlorobutane, both as products. Bromine is very selective. Bromine prefers, if at all possible, to go for tertiary centers, and only if there's no tertiary centers will it settle for a secondary center, and primary centers are not very reactive at all. And so what this will prefer to do is make this molecule. And really, if you're starting with an alkane, that's kind of your only choice, is to do radical halogenation, because we didn't do any other reactions beginning with just straight alkanes. Now, if you look at your product, we have a bromoalkane, but the bromine's in a different position. Bromine's in the 1 position, not the 2 position. So sometimes there's 2 ways to handle this. You could either start forwards from the starting material, think of reactions that'll bring you forward until maybe you blunder across the product, or you can work backwards, starting from the product, and think about a reaction that can make that molecule. And that kind of reverse process is called retrosynthetic analysis. So when I look at this, that product molecule right here, what I kind of think of is if it's a 1-bromo, maybe that came from an alkene that we added HBr to. So if we started with an alkene like that, we could add HBr. However, HBr by itself, we'll add the other way around. It'll give the Markovnikov addition product. We want the anti-Markovnikov addition product, so what we could do is use HBr and peroxides, where R is just some alkyl group. You could think it could be a methyl, it could be a isopropyl, whatever. Probably not isopropyl, it's a little vigorous, its reaction. Anyway, you can think sort of one step backwards. Is there a way to go from there to there? Can we connect the dots now and kind of put this all together? Yes, we can do an elimination here. We could do an E2, and we have a choice here. Is this a Hoffman or a Zaitsev elimination reaction? This one turns out to be a Hoffman reaction, so you want a bulky alkoxide to make it go Hoffman. And so what that would look like would be T-butoxide with T-butanol as a solvent. Let's throw in some heat just to make sure this goes. And there's your sequence. So I guess that's 3 steps. The first one is radical bromination, followed by E2 elimination, Hoffman, followed by anti-Markovnikov radical addition of HBr. So this is from Unit 10. This one is from Unit 6. I guess sort of 7, because we introduced the Zaitsev and Hoffman rules in Unit 7, and then Unit 10 again for that last one. No, wait. Radicals were 9, weren't they? Okay. This one starts us with butene, and we want to go to butyne. The reverse reaction here is easy. The reverse reaction is just using hydrogen and Lindlar palladium, right? If you want to go that way, you can do that. We want to go the other direction. So again, start from your product and work backwards. It turns out there's only a single reaction that we looked at that produces alkynes. And this would start with something like a vicinal dibromide, vicinal dihalide. And this was using that very strong base, let's say 1NaNH3. And in this case, no, I'll erase that. It was NaNH2, 3 equivalents. And just let me move this thing down a bit. Give myself some room here to work with. And our solvent we use is NH3. So NaNH2 is a very strong base. This can do elimination E2. In fact, it can do it on an alkene to make an alkyne. And so these are the conditions. You need 3 equivalents if it's a terminal alkyne, if it ends in a CH, like this one does. And you only need 2 equivalents if it's an internal alkyne. And the third equivalent is because that hydrogen is acidic. And then what we would need to do after we do the 3 units of strong base is add in some source of protons to put the hydrogen back on the CH. So use water or something like that. Okay, so that's a way of making an alkyne. In fact, the only way of making an alkyne that we looked at. Can we go from here to here now? And the answer is yes. This is a reaction that we did back in Unit 8. And so this would be like Br2 with some kind of non-nucleophilic solvent. So we're not going to use water. We're not going to use methanol. Something like hexane would be good. And that would do this overall transformation in 2 steps. Great. If you want more like that, I think there's more that are coming. Again, these are write-in questions from previous years. First one says, fill in the conditions. We call these these questions kind of like roadmap questions. Basically, there's sort of like a series of stops with information missing, and we need you to write in what's missing. So all of the pieces of information that are missing here are given those numbers, you know, looking at 1, 2, 3, 4. And we need conditions for all 3 steps. We need the product after the first step, and we're given the product in the second step and the product in the third step. So the last one maybe is the easiest place to start. You can see what we've done is taken that bond, broken it, we've done cleavage of that alkene, and as our 2 products we get CO2 on one side and we get a ketone on the other side. We have 2 different sets of conditions to do oxidative cleavage. One is using ozone and the other is using potassium permanganate. And the potassium permanganate is done under hot conditions. That's actually the one that we need here, because this CO2 product is what you get from a CH2 with potassium permanganate. If you used ozone, you just get formaldehyde, CH2O. If you used ozone. So we're not going to use ozone, we're going to use the potassium permanganate, which looks like KMNO4, and we use some sort of base. Potassium hydroxide works here, sodium hydroxide, whatever. You do this in water, and we do this hot. So you'd boil this, right? You'd reflux this reaction as it goes. Okay, so we kind of start at the end of this question. We still have spots 1, 2, and 3 to make. If you notice what has gone, we've done this in 2 steps, but essentially what we've done is moved the position of that double bond. So what's likely to happen if you see a double bond and it moves position throughout 1 or 2 steps, usually what we're doing is an addition followed by an elimination. An addition starts with the alkene to make something else, like an alkyl halide or alcohol. The elimination will then remove 2 things and give you back the alkene. So in this case, there's a number of different ways you could imagine doing this. The easiest way is probably if you used HBr. You would do addition. It would be Markovnikov addition. And you would make this. Followed by elimination. And the elimination here, to give you that product, is the less stable alkene. It's a CHEM disubstituted alkene. And so we want the Hoffman elimination. So to do Hoffman, you want a bulky base. I'm trying to think of any other conditions that would work here. I don't think there's anything else. I mean, I can think of some that requires more steps. So for example, if you started with this and you did like 50% H2SO4, you could make this, which, you can't eliminate an alcohol. I mean, you can dehydrate it, but you can't dehydrate it to give you that product, because dehydration, we don't really have Hoffman versions. But what you could do is turn the OH into a good leaving group first by using something like mesyl chloride. This is a chapter 10 or unit 10 reaction. And then going from there, this reaction is not as good though. It adds an extra step. So adding steps generally is a bad thing when you're looking at doing organic synthesis. So you want to do it in the most efficient way possible. But just to show you that there's often multiple different pathways, different routes to get you to the product that you want. I mean, I guess something else that we could have done here, instead of, if we go back to this stage here, is we could go from there to there using PBr3, right? So there's all kinds of different possible routes, and if you provide a route that works and gets there, that's all we'll be looking for. Okay, so the next question says, what would be the best conditions to carry out the following reaction? So what we've done here is hydration of an alkene, and it has given us a racemic mixture, which makes sense. We have a optically inactive starting material, so we're going to get an optically inactive product. And so we need to pick out conditions which do hydration. And so if you look at these reactions, I mean, A is not going to work. A is the one that puts two OH groups on there, makes vicinal diols, as we call them. B, MCPBA, blah, blah, blah. These are not conditions we covered this year. That's not the right answer anyway. These are reactions that make epoxides. The next is sulfuric acid and water. So this is kind of what I was expecting to see. These three conditions are the three different ways we looked at that do hydration. One of these is correct, the other two aren't going to work. And the reason is if you use item D, which is hydroboration oxidation, that reaction, that one, remember, goes anti-Markovnikov, and that'll put the OH the other way around. So conditions D would give you this as your product. So that's not what we want. So D is out. C gives Markovnikov hydration of an alkene, which is what we want. However, C makes a carbocation. In fact, it'll make a nice, juicy secondary carbocation at that carbon right there, which will undergo a rearrangement and end up as giving you a major product that looks like this. So that's not what we want either. So we want the conditions that give the one that's shown as the major product, and that is going to be E. This is the oxymercuration-demercuration reaction. This is the one that works best because that basically does Markovnikov hydration without a rearrangement, which is what we want. Good. Everyone's still happy? If you have any issues with sound or video quality or anything, just pop it in the chat. The chat has like a 15-second delay from what I'm actually saying, so in 15 seconds or so I'll see your comments. The next question, number 11, says, which is the correct lowest energy Newman projection for S2-fluorobutane? So S2-fluorobutane will look like this. That is 2-fluorobutane, and for it to be S, what we would need is that bond to be a hashed bond. So we're looking at priorities. Fluorine is 1, ethyl is 2, this is 3, this is S. So what we want to do is pick out the Newman projection. So first of all, we need to pick one that has 4 carbons. So like B is out because B has 1, 2, 3, 4, 5, 6 carbons. A looks okay, C looks okay, D looks okay, and E looks okay in terms of number of carbons. So what we need to do then is figure out which one of these is the lowest energy conformation. So right away we can get rid of D and E. The lowest energy conformation for like linear non-cyclic compounds is always a staggered one. So it's between A and C. It's not going to be those eclipsed D or E ones. So then the question really is, like, A and C are mirror images of each other. Which one of these is S? And just looking at it, I can see that it's A. How do you know? Well, you have to be able to look at those Newman projections and understand the three-dimensional shape that that Newman projection is trying to represent. So imagine, you're looking at this molecule from the side, and you're looking at it like that. What you would see is this dot is a carbon. This round thing, the big one here, is another carbon that's attached to it. It's behind it, but if you're looking at it from the side, it would appear going off there. And then it has attached to it another carbon, which is that methyl, which is over here. Also, what you would see is this methyl will be pointing to your left if you're looking from that direction. So that would have a methyl there. The fluorine would be going back from where you are. It's going behind. And there's also a hydrogen right here that's coming towards you. So that hydrogen comes out in front. That's that structure. That is S. So part of doing a question like this involves converting between Newman projections and then these more linear structures you see here on the right. Next part, question 12. Ring strain is a combination of which type of strains? So definitely angle strain is involved in ring strain. What else do we got? Torsional. It's kind of a weird question because it's telling you right away it's a combination of types of strain, and then it gives you three answers that aren't combinations at all. Ring strain, from my perspective, it's another way of saying angle strain. I guess technically in rings, this is going to come down to semantics, I know. For this year, if you get a question like this, ring strain is the same thing as angle strain. It's basically the strain you get from causing an angle to be some other angle than what is predicted by VSEPR, right? So you get a cyclopropane, bond angles here are 60 degrees, where VSEPR predicts 109.5, that creates strain. Call that angle strain. So I guess in structures like this, and we went through this back in unit 4, there's also torsional strain all around the ring, which is caused by that shape as well. Okay, the next question is number 16 from some previous exam, I have no idea which. Which reactions would yield a meso compound? So I guess we've got to kind of do these one at a time. Cis-2-butene looks like this. If you did the first one, hydrogenation with nickel, that just makes butane, no chiral centers, not meso. The next one is Br2 with CCl4. What this will do is add Br2 to the alkene, and it'll go anti to give you this molecule, which is chiral. It's not a meso compound because there's no mirror plane. Plus, you'll get the enantiomer of this compound in equal amounts. So it's not A and it's not B. C is cis-2-butene. This is the osmium tetroxide. This does syn dihydroxylation, so it makes a compound that looks like this. And this one, as you can see, has a mirror plane. This one is meso. So this one is going to be correct. You can see the letter here isn't really super lined up well. The other one says trans-2-butene with KMNO4, and it's cold. So this will give you one in front and one in back. No. This is syn. Both in front. And if you do a rotation around there, you'll get this, which is, again, chiral. You'll get its enantiomer formed as well, and not meso. More than one of the above. Not that. The only one that'll do that is C. I hate actually multiple choice questions with options like that. I joked once about giving an exam where, let's say there's like 65 questions, like the exam you guys are getting, and E is always none of the above, and then making it so that the correct answer for every single question is none of the above. That'd be really mean, but don't worry, I'm not going to do that. I can fantasize about being mean, but I wouldn't do it necessarily in real life. All right, major product of the following reaction would be, it's kind of hard to see a bit, but we have an alkyl halide. This is a secondary alkyl halide. We have sodium methoxide and methanol, and heat, and we want to know what we're going to get under these conditions. With a secondary alkyl halide and a small alkoxide, which is what we have here, the reaction of choice is going to be an E2. When you see an E2 and it's on a cyclohexane ring, this is when alarm bells should be going off. There's a special case when there's cyclohexane rings and you're trying to do E2 reactions where you can only use beta hydrogens that are anti to the bromine leaving group or chlorine or whatever. And the reason is that E2 has this requirement that the beta hydrogen and the leaving group are anti to each other. And that has to do with orbital overlap in the transition state and stuff that we didn't spend a whole lot of time on, but it's real and I guess it's important. Okay, so let's look at it. There's a hydrogen here. If that's our alpha, that's a beta, that's a beta. There's a hydrogen there, hydrogen there. The only beta hydrogen that's anti to the bromine is that one circled in pink. So what that means is you can actually not eliminate to put a double bond in that position. What you can do though is eliminate the other way around to make C. That's really your only choice. You're not going to do substitution, it's not going to be D, it's not going to be E, and A is just a poorly drawn version of the molecule in B. So this is something I'm going to give you a warning about, like maybe not a warning, but just put it on your radar. Something not to do. If you have an sp2 carbon, like that's a carbon that's part of a double bond, like an alkene or an aromatic carbon, don't use dashed and wedged bonds from an sp2 carbon. They are flat, they are trigonal planar in shape, so they should look like they do in molecule B, flat. No dashed or wedged bonds from an sp2 carbon. While I'm on that topic, no dashed or wedged bonds either from a cyclohexane chair or a Newman projection. So the dashed and wedged bonds are a way of showing three-dimensionality, three-dimensional shape. The other one that gets me is if people draw things like this. To draw an alkyne. These are sp carbons. sp carbons have bond angles of 180 degrees. So this should really be looking like however many we got here. 1, 2, 3, 4. 1, 2, 3, 4. So yeah, those types of bond angles make my eyes bleed. And that looks bad too. So please don't draw them like that. If it's sp2, no dashed wedged. If it's sp, just a straight line. Just bond angles of 180. All right. Which molecule would undergo the fastest E2 reaction? Oh no. Okay, all of these are secondary alkyl halides, and all of these are cyclohexane ring structures. I wonder, I wish I left myself some more space. Basically what we're going to be doing is for every single one of these examples, drawing a cyclohexane chair and seeing if which one has the most stable conformation with the bromine in an axial position. So if you look at molecule A here, I wonder if I can just add myself a sheet in here somewhere. Give me a page right here. Add page. Okay, so we're up here, we want to do A. So A looks like this, and so if you draw cyclohexane chair for this, and if you looked at, say, this being carbon 1 and carbon 3, carbon 1 and carbon 3, we see the bromine is up, and it's hydrogen down, and the down here is the isopropyl with the hydrogen up. Actually, that's not so bad, right? That structure actually looks pretty good because the large group is equatorial. So this is going to give a very fast reaction because the major conformation has the bromine in an axial position. Okay. The fastest reaction will not occur with the least stable configuration. It'll only occur with the configuration that has bromine axial. So what you want is so this will have another ring flipped form, and that ring flip form is going to look like what? This. So that Br comes down here. It'll look like that. This one will have no reaction. Fortunately, the large group here, the isopropyl, makes that conformation unstable. So I don't know what the numbers will be. Maybe that's 80% of the time, and this is like 20% of the time, or maybe it's 90-10, or maybe it's 99-1. I don't know. But what you want is the major conformation to be the one that's sort of in the reactive form. The reactive form is when the bromine is axial. It has nothing to do with the, an unstable molecule reacting faster. Is it set up most of the time to be in a shape where it can react? So I'm just going to pick, I think I stumbled across the correct answer right away. But if you instead look at molecule B, molecule B was this, I think. So this molecule, if you draw cyclohexane chair, the bromine is up and the isopropyl is up, and if you draw the ring flip form, you get bromine over here. I kind of moved positions there, didn't I? I moved positions up here. So this will be the Br here. This will put the isopropyl over there. Didn't draw a great ring here, but this is very stable. Both groups are equatorial. So this is like 99.9% of the time, 0.1% of the time. This is the only form that can undergo the reaction because this is the only one with the bromine's axial. So this overall is going to have a very slow reaction because it's almost always in the conformation that cannot react, which is this one over here. As opposed to this one, where most of the time it is in the conformation that can react. And we could do the same thing. We could draw all of these examples, but what we're going to find is the best one is going to be, I guess, A. None of the other ones look very good. Yeah, D, I can tell when it's trans. When the two groups are trans, same for C and E. If it's 1,2 or 1,4 disubstituted trans, the best conformation has them both equatorial. So yeah, not C, not D, not E, and not B. A is good for that reason. Is that clear? If not, I can do something like with it more. Next question says, what would be the major product of the following reaction? This is a tertiary alkyl halide reacting with methanol. Methanol is going to likely act as a nucleophile here. If you heated the thing, then we would say elimination would probably be major, but there's no indication that this is being heated. And so what we do is we replace the Br with OCH3, and we get B as the major product. C would be like the elimination reaction, which is probably going to be the next most important product. A you cannot make. If you're adding an OH, you need water. If you're adding an OCH3, you're using methanol. D somehow added a carbon. It's not D. And E replaced a CH. It's not that either. right. What's that, Catherine? VOT, FYI. The next reaction is this one here. This one was sent to me as a screenshot from previous exam. This one is, again, this one is on the list of things that we are canceling for this particular year. So yeah, this is a carbene reaction. We actually did this in my section, but we didn't do this particular, in the other section, in section B, that class didn't do these cyclopropane synthesis reactions. So it turns out these are not going to be on the exam. Just that one reaction from Unit 8, which is addition of a carbene to a double bond to give you cyclopropanes. So that one you can ignore. All right, everyone's happy? Give me a thumbs up in the chat if everything's good. All right. So the next reaction, or the next question is this one in blue. And what this question is asking for is, it's looking for the conditions to make this reaction happen the way it seemed to happen. And if you look at what's gone on here, there's an obvious rearrangement, like the positions of the carbons have changed going from the starting materials to the products. We've done addition of HBr, but it proceeded in a way that gave us a carbocation at some point, because of a carbocation form that allows for the rearrangement to happen. So this is, I mean, just HBr is the only thing that needs to happen here. Maybe they wanted a mechanism too, but what happens? I didn't actually get the question part of this. All I got was the picture. Okay, I got a thumbs up. Thanks, Leah. This would do a reaction like this. This would put a hydrogen and it would put a positive charge on that carbon, which is secondary, plus bromide, like that. All right, once that's formed, the secondary carbocation can undergo a rearrangement, and it'll undergo a rearrangement if that helps it become more stable. So the rearrangement here looks like that. We start the arrow between the two carbon atoms. We started at the bond, because the bond is moving and it's carrying the CH3 over with it to produce this. And now the plus charge is over on that carbon. Next, the bromine can attack once you have that more stable tertiary carbocation, and you make that product that you see over there. Great. Good. Next reaction. What's going on in this case? The answer is circled. This comes from the answer key from a previous year. NaNH2, what's that? Okay, NaNH2, what that is a very strong base. Again, we see sodium here as a sodium compound. Sodium dissociates away as Na+, leaving behind NH2-. Looks like that. And this is a very strong base, a stronger base than hydroxide, a stronger base than alkoxides, stronger than any of those things. And it's in fact strong enough to deprotonate a terminal alkyne, which is what we have here. These are sp carbons, that's an sp3, and that base will come along and pluck away that hydrogen, and what that'll make is a carbon which has a lone pair, a triple bond, and a negative charge, and we call these alkynides. And these are, first of all, they're good nucleophiles. Second of all, they're good bases. So if you see one of these things, think in your head, it's essentially similar in reactivity to a small alkoxide. when it comes to reaction with alkyl halides. So what that means is if you have a primary alkyl halide or a methyl alkyl halide, it'll do SN2. If you have secondary or tertiary, it'll do E2. So this has step 2, and in step 2, we are taking that alkynide that we just made and we are reacting it with CH3I. And remember, iodide is a fantastic leaving group. Methyl halides are the fastest for doing SN2 reactions. Everything here should be screaming SN2, so that will attack the carbon. You lose iodide, and that makes molecule B plus I minus. That's it. That's what's going on in that particular reaction. So notice the product of A, that's what's formed after just the first step in that two-step reaction. So make sure that you're paying close attention to the conditions and that you follow it through all of the reaction steps that are shown there. All right, everyone's favorite, some more multi-step. This one says, outline a multi-step, 2 or more steps to carry out one of the 2 chemical transformations. We don't want mechanisms, all we want is the reaction conditions with products. And we start with this alkane. So luckily, if you get one of these kinds of questions and you see yourself starting with an alkane, you should celebrate, because there's only one reaction we know that starts with an alkane, which is radical halogenation. So we're going to be doing a chapter 9 radical halogenation on this particular molecule. We have 2 different kinds of carbons. We have a tertiary carbon and we have several primary carbons. So what we want to do is pick conditions. We only have ones that are selective for the tertiary. Or a chlorination will go random, bromination will go selective. So if we do Br2, let's use light this time, H nu, Greek symbol nu. They skipped nu, by the way, for COVID-19, because you know how it's on Omicron? When they were going through the letters, they skipped nu, because they thought if it was like the new variant, people would think it was NEW. Anyway, that will replace the CH in the middle with CBr to make this. That's not quite there. If I look at that molecule, what I see is that probably came from, well, I guess the arrow should go the other way around. That probably came from this, which did anti-Markovnikov addition of water. So this is hydroboration oxidation, and if you forget the conditions in a reaction, like in a question like this, and you forget exactly how to write it out, look in the previous sections. Like for our case, look in the multiple choice section, see if it's drawn out somewhere for you. This is BH3 and BH3 with THF, which makes like a Lewis acid-base complex. THF is your solvent there, followed by the oxidation, which is hydrogen peroxide along with NaOH. So we can close the loop here by taking that bromo compound to the alkene by using any old elimination conditions we want. Turns out any elimination conditions will do this. We could do E1, we could do E2. Generally, if we have a choice, we pick E2, because E1 is often contaminated with SN1. So let's find some conditions here that'll do E2. How about a small alkoxide and heat? You could use a large alkoxide and you'd get the same reaction. So either one is okay in this particular example. All right, so there's another one like that here. This is got a bromo on carbon 2 and an alkyne on the end of the chain. It's usually good in these examples, especially if there's an alkyne, to count your carbons to make sure this is the same. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's good, because alkyne reactions will often add carbons. but not in this case. We have 5 and we have 5. So I like to think backwards in this case. We only know one reaction, again, that'll make an alkyne. And that would start with something like a vicinal dibromide. This is with your NaNH2, 3 equivalents, to some source of proton to put the hydrogen back on that end carbon up there. So that's just water. Sometimes you say water and acid, or just water, just something that can put the hydrogen back on. So that gets us to here. We know how to make vicinal dihalides as well. I don't know why that looks super ugly. That alkene will do that using Br2 and hexane, or carbon tetrachloride, or chloroform, or some other non-nucleophilic solvent. Finally, we need to go from there to there, which is an elimination with an alkyl halide. It's an E2 elimination. That E2 elimination is Hoffman. So with a Hoffman elimination, like the one you see here, you want to use a bulky base. And heat. Cool. So that actually is it for questions that were sent to me. What I can do is briefly check my email to see if nothing else was sent. Let me see what else I got here. Oh, I was asked by email to do an example with potential energy diagrams. So, potential energy diagrams basically look like this. There's a scale, there's energy, and on this scale it's sort of like extent of reaction. And every one of the reactions that we look at have every one of our reactions that we look at obviously will have a potential energy diagram. Potential energy diagram matches up with the different steps in the mechanism. The number of humps that you see in this potential energy diagram is equal to the number of steps in a reaction. So if you look at something straightforward like an SN2, where if you have a nucleophile like cyanide, the mechanism is very straightforward for something like this. And look, it makes my favorite solvent as a product, acetonitrile. This has one step. It has one transition state. So if you had a question, can we send it in an email? Yes. Please email me questions now if you still have questions that you'd like to see done. So an SN1 reaction, or sorry, an SN2 will look like this. So your starting material is somewhere down here, and it'll look more or less like this. So it'll have a single transition state. This will be your activation energy. Your products over here, and that's that. I do see a few questions up here in the chat, which I'll deal with in a sec. If you have an SN1 reaction, this mechanism has two steps, and then we take some other nucleophile, like, I don't know, let's say we're with an iodide, bromine goes out, iodide goes in. This would have a potential energy diagram with two humps. where you have your starting material. And notice how this one starts out, that's a transition state, that's a transition state. This is your carbocation up here. And it's much higher in energy than either your starting material or your products. And I don't want to go through this with every reaction example that we have, but think about these chemical steps as we do them and the different potential energy diagrams that go with them. In most examples, we looked at the potential energy diagrams for each one, and there's a question like that on one of the midterms too. Clara, see your question. Joseph, E, none of the above. Multiple choice could be interesting. Yeah. Interesting is one word for it, for sure. Holly asks, is there an easy way to remember which reactions do anti-mark, mark, and syn anti-addition? For the ones with mechanisms, if you know the mechanism, which way it goes is very clear. So if you look at the Markovnikov ones, this was like anything with the mechanism ADE2, which is electrophilic addition, like an alkene plus HX, or an alkene, by the way, this will make something like that, plus it's like 50% H2SO4. This will do hydration. Both of these are Markovnikov. In addition, we did the other hydration, which was oxymercuration, demercuration, which is also Markovnikov, and the other way around, the anti-Markovnikov was the hydroboration oxidation. I guess the easy way for Markovnikov is there's only two reactions that are anti-Markovnikov. One of them is hydroboration oxidation. When I say there's only two that we covered, right? We only covered certain reactions. The second one that we covered was radical addition of HBr. That's also anti-Markovnikov. So those are the two reactions that are anti-Markovnikov. Yes, anti-Markovnikov. All other addition reactions are Markovnikov. For syn and anti, the only anti reaction we looked at, and I don't mean anti-Markovnikov now, I mean anti-addition, is addition of like Br2Cl2. So that's the only one that's anti. All of the other ones are either syn or neither. So the ones that are syn are hydrogenation using metal catalyst, hydroboration oxidation was syn. What else do we do that was syn? Anything with a carbocation will not be syn and not be anti. You'll get 50-50, or something close to 50-50. Oh yeah, we did a few other syn ones, like we did put potassium permanganate in the cold will give you the cis diols, syn addition. Hopefully that covers it. I heard my email bling a couple of times here. Okay, so I see a couple more questions. The exam is being written in the gym. Yes. 9 o'clock. Tuesday. Chloe says, which way does the equilibrium lie? And the question looks like this. Something like that. And the answers are to the right, to the left, neither it is equal cat or dog. So it's not cat or dog. Hopefully that much is clear. And basically what you want to do for any of these equilibrium questions, it's always an acid-base problem, and it will always lie towards the side that is a weaker acid and a weaker base. It wants to make the weak things because those are more stable. Strong things are less stable, that's why they're more reactive. So the difference here is this is an sp molecule. You could draw in our remaining hydrogens if you want. This one is an alkene, this is sp2. Versus this, lone pair there. So the question really is, what's a stronger acid? An sp2 carbon or an sp3 carbon? And the answer is the stronger acid is the sp carbon. I said sp3, I meant sp. Sp is a stronger acid than sp2. Therefore, it's going to lie towards the left. You might use an equilibrium symbol that looks sort of like that. Lies towards the left because it wants to lie towards the weak side. In other words, this thing is a much stronger base than the base on the left-hand side. In fact, you'll never see a base like this, certainly not in this course. These are extremely reactive, extremely difficult to produce. But these ones aren't so bad. We've seen these ones before. We can make them. They're pretty stable, relatively speaking. I mean, they're stronger bases than like hydroxide, but yeah, not super strong. All right. More questions. Okay, I see one. This one comes from 2016 final exam. It says, draw 1R, 2S, 1 bromo, 2 ethyl, cyclohexane, convert it into the chair, do a flip, and then react it with C via the provided conditions. The provided conditions are NaCN in DMSO. It screams SN2, doesn't it? And then convert the product back into a flat template. So we're drawing a regular structure for this molecule, turning it into a cyclohexane chair structure, and then we are going do a reaction on the chair, turn it back into a regular compound. This nomenclature, by the way, we didn't really stress much this year. In earlier years, we used to do a lot more with nomenclature. So I'd probably give you the starting structure here, or at least give you the structure and you determine the RNS. But if we begin, this is a cyclohexane, and we have a 1 bromo, 2 ethyl, and we got to give it the correct stereochemistry here. So if 1 is R, that means this bromine is going to be coming forward, and going in back is a hydrogen. The 2 ethyl, if the 2 ethyl is S, what do we got? 1, 2, 3. This is also forward, I believe. So if they're both coming forward, we need to draw this as a cyclohexane chair. Which looks like that. We could pick any 2 carbons we want. Actually, we can't. It tells us that this is 1 and this is 2. I didn't leave myself enough space, so let me just move this over a bit. Okay, so carbon 1 and 2, this is carbon 1 and carbon 2. Carbon 1 has Br as up, this has the ethyl as up. Carbon 1, the up position is over here. The down position is the hydrogen. Carbon 2, the up position is ethyl, and the down position is over here is hydrogen. So that's the correct way to draw this molecule. This will have a mirror image. Where this is 1 and this is 2. Br is up. Again, I'm not leaving myself much space here. Maybe I can, no, I don't want to do that either. Wrong button. Okay, bear with me. Okay. Carbon 2, the up position is there, and the down position is the hydrogen. I've stretched that out a bit just to make that obvious where it is. And on this, we want to do NaCN, DMSO. DMSO is just a solvent, polar array product solvent, and we have cyanide, and this is going to do an SN2, we said. It does that. It does an inversion of that carbon. And so what that means is it pushes the hydrogen up and the CN is down. The other carbon stays the same, like that. And now it wants us, as our final step, to flatten it back out again, which we can kind of cheat. We can just redraw our starting molecule and do an inversion where the Br was. Just like that. And that gives us our product. Great. Okay. So let me just bring back my screen here. Was there a reaction covered for anti-addition of H2? No. There's no way to add H2 anti to an alkene. There is a way to do addition of hydrogen anti to an alkyne. So if you have a triple bond, you can use the dissolving metal reduction, which is ammonia in NH3, 1, 2, 3, 4, 5, 6, to make the transalkene. So this is the fourth reaction we looked at in Unit 8, and it's the dissolving metal reduction. Cool. All right, some more questions. Could you go over number 6 from 2019 fall multiple choice exam? I do not understand why 3 and 4 are not considered constitutional isomers. So let's bring up 2019 exam. Okay, I got them all right here. I'd hate to accidentally bring up this year's exam. Oh, there it comes. So I'm going to pop that down. And bring this over. So the question here has to do with, by the way, this is the Scantron that we're going to be using, exact same sheets. Not that far. Question 6. Do I have the wrong question? This does not look like a... Number 6 from 2019 fall multiple choice. Is it a choice exam? If there's something I'm missing, because I think this is the file 2019 final exam. That's from Allison. So Allison, if you're listening, I think something's crossed in communication here. Just try sending it again. I do have a question here from Victor, and that was from the 2019. Is that still, did I close it? No, that's 18. I'll just bring it over, look. There's my question by email. So that's the one we want to do. We want to say what reacts with tetrabutyl ammonium fluoride in THF to give you that molecule. So let's slide my email back where I can read it. And let's zoom in on that. Okay, so the question wants us to do Bu for an F in THF to give you OH. So these conditions, by the way, there's a couple of different ways we sometimes write them out. Another way we sometimes write this out is as just TBAF. TBAF is tetrabutyl ammonium fluoride. So these are the same thing. These are conditions that we would use to deprotect a silyl ether. So if you have an alcohol and you react it with TBDMS Cl, for example, and you made a silyl ether that protects the alcohol, it makes it sort of immune to reactions that alcohols would normally do. This deprotects it. So what I'd be looking for here would be a molecule like OTBDMS. And just looking at the options that are available, that looks like D in that particular question. Instead of giving the abbreviation, it actually writes it out as Si methyl T-butyl. So these are the same thing. So the TBDMS is tert-butyl, which is this thing. DM is dimethyl, and then the S is silyl. That's really what that's getting at right there. Okay, another emailed question popped in. A few questions. They're based off old midterms. When you have a syn addition and there are previous functional groups in the molecule with no wedged or dashed bonds, should you make those dashed and wedged bonds? Okay, so I guess the answer to that question is it depends. When should you use dashed and wedged bonds? I would say you should use dashed and wedged bonds anytime stereochemistry is like a consideration. So what's an example? So let's say you have alkene with 2 methyls there, and you want to do some reaction with syn addition, like say hydrogenation. Let's use rhodium, and what that's going to do is syn addition of H2. What we should do is in our product indicate that the product worked to give us a syn addition. Like that. Okay? So that would be a correct place to use it. Where would be a correct place not to use it? Well, if you have something like this, same reaction. I'm not using dashed or wedged bonds anywhere there because there's no chiral centers. There's no possibility of diastereomers. There's no cis, there's no trans, none of those things. So in some cases you should put it, in some cases there's no point, right? And so that's what I would say. If there's no point in doing it, don't put dashed wedged. So like, yeah, if you did this and you have something like, that just looks awkward. So yeah, don't do it in a situation like that. The next question. Okay. Next question for you, Clara. There's an example with addition of Br2 in water to an alkene. The question is, do I have to do it the way it is shown in the answer key, or can I do it the way I've drawn it? And so she draws it one way and it's drawn a different way in the answer key. From what I can tell, both are correct. So there's multiple, generally speaking, there's multiple correct ways of drawing almost anything. So the question was around an addition like this, where you're adding Br2, where there's a, the first step looks like that, and Br plus. There's lots of different ways you could draw this. Like you can see the way I've drawn it, a little bit messy there, but it's showing the Br is coming out towards us. You could also draw that like this. Those are the same thing. Both are correct, both are acceptable. You can draw it basically any way you like. Curran says, can you please go over written question 6b from the 2018? Sure, I will in a sec. I think there's a few more in Claire's email. This is a reaction starting with a primary alcohol, and this is PBr3 HBr or either, and PBr3 is circled as the best way to do this reaction. As far as I'm concerned, either one is okay. I think there's some special cases that we didn't talk about where if you have methyl alcohols, they actually don't react super well with things like HBr for some reason I can't remember. But I wouldn't get caught up with that. If you gave either one for me, I'd be okay with that particular example. Next question looks something like this. It's an alkynide, and it's saying that's the reaction product. Why do you get that? How do you explain this particular reaction? Well, this is an alkynide. Think in your head, it's equivalent to a small alkoxide. They will do SN2s if you react them with a primary alkyl halide, but this one's secondary. This is going to do E2. Just think of that negatively charged triple bond carbon, that alkynide, as the same as a small alkoxide. It'll do the exact same chemistry. Next question, I'll get to yours in a second, Curran. Oh, these ones are tricky. And this one is saying Na plus, and it wants to know what the product is. It's going to be E2. It's going to be Zaitsev's rule, and so there's going to be a double bond generated there. What has to happen is that chlorine, the leaving group, and the hydrogen, because it's E2, have to be anti to each other. This is a big concern when you're on a cyclohexane ring, but in examples like this, it's also a concern when you're doing, now you have free rotation with all your bonds here, so you can adopt the correct conformation quite easily. But what we need to do is rotate it so the hydrogen is anti to the chlorine. So if the chlorine's in front, the hydrogen needs to be in the back. So what we're going to do first is just rotate. We're going to leave the Cl where it is, and if we rotate it so that that group comes up, right, the hydrogen that's in front is going to be going in back, and the methyl that was in back is now in front. Now it's okay to do our E2. And that will give us, as our product. So this ethyl and that methyl are going to be cis to each other, or I guess Z to each other. So this anti-requirement for E2s can also occasionally be a problem when you have a cyclic chain, like in this example. This question, next one, is talking about stability of carbocations, and it gives this one versus this one versus this one versus this one versus this one. And it wants to pick the one that's most stable. Right away, we could probably X off that one, which is a primary carbocation. That one's a primary carbocation. Those are really ugly here. This one is secondary. This one looks bad. This one looks primary, but it's actually not that bad because this one has resonance structures. So this one has a resonance structure that looks like this. And so what that does is it spreads that charge out over two atoms. Whenever you have resonance structures, it stabilizes the structure, especially when you have ions. Stabilizes the ions by having those resonance structures. This is called the allylic cation. It's actually fairly stable. And if that's not so bad, this first one is actually even better, because this one has a resonance structure like this, charge there, and there's another resonance structure like there. So this one has three different resonance structures. Those double bonds adjacent to the carbocations make the carbocations far more stable. This is a big part actually of Organic 2 when you get into that course, making carbocations much more stable through resonance. Basically, the more resonance structures, the more atoms the charge is spread over, the more stable it's going to be. Okay, this was another question. Again, Curran, I still got you coming. This says which of the following molecules will be polar, and the choices are CH4, CO2, C2H2, CH2Cl2, and CF4. So CF4 and methane are both nonpolar. They're both perfectly symmetric tetrahedral molecules. CO2, perfectly symmetrical linear compound. C2H2 is a perfectly symmetrical compound as well. So everything cancels in those four. CH2Cl2 has this structure. Which will have a net dipole that goes in that. So this one is the only one of them that is not nonpolar. Now, that's to say, this is a weakly polar solvent. Technically, when we look at our types of solvents, where we have polar, aprotic, polar protic, and nonpolar, we would classify this one with the nonpolar ones. And that's because if it's weakly polar, there's a measure of something called the dielectric constant. If the dielectric constant's below a certain number, we call it nonpolar. This falls below that number, but the polarity definitely is not zero. I think we got one last one in this set. And this last one is saying which of the following reactions would yield an achiral molecule. This, two equivalents of Br2 in dichloromethane, Cl2, and this makes and that's achiral, no chiral centers there. The next one is the same molecule with NaNH3, that's the dissolving metal reduction. We'll make that molecule also achiral. The next one was this using KMnO4 conditions and cold. This will make where if you rotate that around, this one's chiral. You'll get this and it's an enantiomer at 50-50. Okay, so the first two both yield A chiral molecules. So A and B are both correct answers. All of the other ones actually give you chiral molecules. So yeah, this is a weird one. It's got two correct answers. I'm not sure what was they were going for in that particular year. Okay. Curran, I've been waiting long enough to do your question, so let's get back to that. You wanted 6B from the 2018 exam. 2018. Question 6. Which part did you want again? B. Okay. Question B. Okay, so this one starts with Br2 and methanol. So methanol is a nucleophilic solvent, and it says show the complete mechanism and final product for the addition of Br2 and methanol. Show stereochemistry where relevant. Okay, so we want a mechanism here. Let's put our bromine molecule in. We do this addition, that should point to the bromine, points to the carbon, points to the bromine. Makes that carbocation. Next, we have our nucleophilic solvent, methanol. We have bromide as well. So like bromide could come in and react, but it's going to be overwhelmed here by the methanol because methanol is a solvent. It's going to be present in much, much higher concentrations. And so what this is going to do is attack via nucleophilic attack the more substituted carbon, because when you have these positively charged three-membered rings, you know, these, we call them bromonium cations, that they actually share that positive charge with the two carbons it's bonded to, and the more substituted one takes more charge. And so that's a better, it's more electrophilic, it has a better target for our methanol. So it'll attack there and open up our ring. That'll put a Br there. That will cause an inversion. So, I mean, I guess another way I could draw that is up here. That's attacking from behind, so that's going to push CH3 in front. It's going to look like that, positive charge. We don't like products that have charges. So what we'll do is remove that. Br, that, OMe. So that's the answer. This is a chiral molecule. You know, we've got a chiral center there and there. You're also going to do the exact same thing with the bromine adding the other way around. So if you think of this instead over here, this is going to go through the same sequence of reactions as the one I drew to give you the enantiomer, the mirror image of the molecule we got over here as our final product. And you'd expect to get 50-50 of the two products. You get a racemic mixture because we're starting with achiral molecules. So if you're starting with an optically inactive mix, you're going to get an optically inactive mix of products too, which generally means racemic mixture if you are making something that's chiral, like we are in this case. Okay, Allison's question is back again. She meant question 7, and it says, which of the following represents a set of constitutional isomers? These are our molecules. And what we need to do here is, I would say in each case, come up with the molecular formula. So this one, cyclobutane, C4H8. This one, we have, again, 4 carbons, 2 methyls, 3 plus 3 plus a CH2 gives us 8. So that is one example. This molecule over here on the right is still C4, and there's CH2, 3, 4, 5, 6, C4H6. This molecule over here has 1, 2, 3, 4, that's C4H6 as well. And this one is C5H8, I'm going to guess here, 1, 2, 3, 4, 5, 6, 7, 8. That's right. So, which of the following molecules constitutional isomers? Constitutional isomers are ones with the same molecular formula but different connectivity. So, I mean, this first one is out of the running. It's got nothing with 5 carbons. Of the remaining ones, I guess kind of what we have here is 2 sets of constitutional isomers. Those 2 are constitutional isomers, and also those 2 are constitutional isomers. So our answer is 2 and 5, which is correct. But 3 and 4 also are. Maybe this is the source of the question. If that's the case, Allison, that's possibly an error in that previous exam. What year is that? I bet you it wasn't one of mine. I wouldn't make that mistake. So yeah, that is, there's multiple correct answers to that question, except I guess 3 and 4 isn't one of the options. So I guess it's not really an error, it's just that there's more than one correct answer and the other correct answer is not listed. Holly asks, draw the major products for the following reaction, including stereochemistry if relevant, like always. The molecule looks like this. And we are reacting this with NaCl and DMSO. This is a straightforward reaction. It's an SN2. The complicated part is this OTS, which is pretty new to us so far. This is a tosylate. This is those versions of alcohols, we call them sulfonate esters, that turn the alcohols into amazing leaving groups. So if you see OTS, or if you see OMS, or you see OTF, those are tosylate, mesylate, and triflate. Almost in your brain, think about that as being the same as if there was an iodide there. The reactivity of these sulfonate esters is a lot like iodide. In fact, they're actually better leaving groups than iodide. So if you reacted either one of these with NaCl in DMSO, you're going to get an SN2. And that's going to substitute the group, kick it out, replace it with a chloride, and invert your stereochemistry. Because SN2 always proceeds with inversion. So that's your question, Holly. I see no more questions in my email or in the chat. If anybody has any questions, I'd be happy to entertain them. So I'll wait around for a minute or so. If you emailed me a question and it's on the way here, you just let me know in the chat, because the chat I'll know in 15 seconds. The old send receive button. Nothing. Okay, that might be it then. I can see my viewership starting to fall off too. Not too bad. We peaked around 60 people, 70 people, and we're down around half that now. I'm going to call this quits. We had a good hour and a half. I think we dealt with a lot of questions. If you have additional questions, please feel free to email them to me. I may or may not get to them. I still have to prepare another exam for another course for the same day as our exam, and deal with all the printing and collecting and everything for the actual exam we're writing. Oh, look, a question just popped in. When is it applicable in questions to flip chair molecules given to get the correct answer? In terms of chair flipping to get the right answer, obviously if I ask you to draw it and flip it, then that's one place. For reactions, the only time you'd ever have to flip a chair in a reaction would be, unless specifically asked, you could flip a chair if you're doing an E2 on a cyclohexane ring and you need to get the leaving group into an axial position. Then you could flip the chair, put it axial, and then you could do it. And Chloe says, would it be an option to drop one of our midterm grades and put the weight on the final? Absolutely yes. I will do that automatically, if that helps you. Great, getting some thanks here. Thanks everyone for popping in tonight. This recording will be available afterwards, and we'll see you everyone on Tuesday.